My whole philosophy on learning how to interpret NMR spectra is to learn how to drink from the fire hose, and that means start with the simplest things and work your way up. Now, it's critical that early on in the class we begin to learn how to interpret NMR spectra. And so we're going to start to see unknowns where you have something like the formula given and be asked to figure out what is the structure. That is one of the primary uses of NMR spectroscopy in the science of chemistry. Now, very often when folks are learning NMR spectra, they will often want to start with the coupling patterns, because let's face it, that's where all the sex appeal is in NMR spectroscopy. Doublets and triplets and quartets, oh, that's so much fun. And oh, it is a whole lot of fun, and we're going to learn about it. They will also want to start with chemical shifts and try to interpret what's the difference between 2.3 and 2.2 ppm and try to make big elaborate arguments based upon that. And we are certainly going to be learning about chemical shifts. But very often, simply thinking about groups and integrations, just how many resonances we see and how do they integrate, can often be enough to get a lot of information about your molecules, and that is often the simplest thing to look at. So that's where we're going to begin. We're going to look. I'm going to do two examples of molecules where we know the formula, and with a little manipulation about the formula and one bit of chemical shift information we've already talked about, knowing where aromatic molecules come, we're going to be able to solve pretty good sized molecules based only upon looking at that information contained within an NMR spectrum. And as we move along, of course, we're going to get to more and more sophisticated molecules and drink out of, use more of the fire hose of information than an NMR spectrum gives us. But we got to begin somewhere. Groups and integrations is a good place to begin. So one thing to think about when you are doing this type of work and you have the formula is one of the most critical things is the unsaturations. If you know the formula, or you can derive a formula from other information, you can calculate the index of unsaturations. Remember from your basic organic chemistry, an unsaturation is a pi bond or a ring, okay, or a combination of both. Classic example, C6H6 benzene, okay, with that structure, alternating single double bonds traditionally drawn. Now, there's a cute little formula for an index of unsaturations. There's a lot of versions of it. I'm going to use one of the simplest ones I know about because it works, really well for a lot of basic molecules. And that is simply the index of unsaturations is the number of carbons minus 1/2 the number of hydrogens plus the number of halogens, chlorines, bromines, iodines, fluorines will fall into that category, minus number of nitrogens. And frankly, phosphorus would usually work there, or elements of that column of the periodic table, plus 1 on the formula. And there's the formula for the index of unsaturations. Now, using benzene as my example here, what we do is we take the number of carbons, 6, minus 1/2 the number of hydrogens, 6 of them. There are no chlorine or no halogens, no chlorine or bromine. There are no nitrogens, plus 1, okay? So 6 minus half of 6, 6 minus 3 plus 1 is 4, okay? 4 unsaturations, 3 double bonds, okay? 3 pi bonds, and the ring, 4 unsaturations total, okay? And that's a useful bit of information to know about, especially in examples when you're given formulas, and that's what we're going to be looking at next. So, we're going to look at 2 unknowns from the formulas, and I'll have the spectra here as well. The PDF copies of the spectra are linked in the description of the video that is posted on YouTube and also available on the course website, because sometimes having the actual PDF on paper or on your own computer screen is a lot easier than what you'll see here. So take those if they're useful, and away we go. First unknown. The formula is given as C7H14O. Okay, so there's the molecule here. If you're given a formula, it's always a good idea to do the index of unsaturations. Number of carbons, 7, minus half of the number of hydrogens, 14. No halogens, no nitrogen, plus 1. 7 minus half of 14 is 7 minus 7, plus 1 is 1. 1 unsaturation in this thing. And so it can't be an aromatic molecule, okay? There's not nearly enough unsaturation, but there is either a ring or a double bond somewhere in this molecule, okay? So right off the bat, we know that information. Now, we take a look at the proton and the carbon spectra, and what we're going to be looking for is what, from the spectrum itself, number of hydrogen groups, their integrations, and the number of distinct carbon, okay, number of distinct carbons, okay? That's the information we're going to glean from looking at the spectra. So here they are. Looking at the hydrogens for a moment, okay, we seem to clearly see 5 groups, okay? Now, overlap can be an issue here, so there could be more, but we do see 5 distinct groups. We look at the integrations, and the integrations are sometimes not the world's prettiest whole numbers. This is a real sample, and there is actually some slight contamination in it, which makes some of the integrations a little bit higher than they ideally would be. That's okay. We have to learn how to deal with that sometimes, but we're going to, use the idealized integrations from 3 to 6 to 2 to 2 to 1, okay? And one quick confirmation, we look at those integrations and see 6, 7, 8, 9, 10, 11, 12, 13, 14. It adds up to the number of protons in the molecule, so we aren't missing anything. And the integrations, seem to be reasonably accurate. They're not twice as high or half as much as what we have here. So that works out very nicely. Looking at the carbon spectrum, and again, we ignore the solvent peaks, and there is a small solvent peak in the proton spectrum, and it's clearly marked on the spectrum provided. And there is a solvent peak of the carbons. We ignore those. They're not anything we look carefully at. But looking at the remaining carbons, not the solvent, we see 7 of them. Okay, there are 7 distinct carbons. 2 of them are fairly close together. Okay, but they even on paper they look they look distinct, and that is exactly the number of carbons here. What that tells us, what you should take away from that really quickly, is that this molecule is not symmetric, okay? There is no symmetry in this thing that is rendering groups of protons and groups of carbons equivalent to each other, okay? Because we see all 7 carbons. If there were symmetry, we would see a reduced number of carbons, as some of the carbons are on opposite sides of a mirror plane or other element of symmetry. Okay, so that's the information we have available to us right now. We already know it's not aromatic because of the index of unsaturations, but clearly we look at the chemical shifts in there and we see nothing around 7, which in the proton spectrum is a clear indication of aromatic. There are a variety of peaks in there, and and one up around 9 ppm is really telling us something important, but we're going to save that for later. Now, some people, seeing this have had experience, or at least a little bit with NMR before, and you'll have a pretty good idea of what that means, and that's wonderful. But based upon just the index of unsaturations and groups and integrations, we should have a pretty good idea of what this molecule is, okay? And the 6 here is certainly not 2 methyl groups. It is, you look at the spectrum, it's kind of an ugly looking thing, a pile of stuff. It certainly overlaps. And almost certainly it is CH2 groups that are overlapping here. So there seems to be a CH3, a methyl group, lots of CH2s, at least 1, 2, 3, 4, 5 of them, and then a single hydrogen. Putting all that together with our intuition, 1, 2, 3, 4, 5, 6, 7, okay? There's a string of 7 distinct carbons. We're going to have to make sure this thing is not symmetric. And in fact, if I put in the hydrogens, and no, I'm not going to belabor putting in writing in all the little H's at the moment. There's hydrogens in those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. That's all 14 hydrogens, all 7 carbons, okay? And in fact, each of these is saturated, so I still have an unsaturated and the one unsaturation and the one oxygen to go. It's going to go out here, okay? Double bond, oxygen. Okay. And what that renders is this is an aldehyde. Okay, there's a carbonyl with one, I'll go ahead and draw that one in, one hydrogen at the end. Okay, and in fact, this is heptaldehyde. Okay, heptaldehyde. Now, when I do these sorts of things, and I examine unknowns in my own research, or helping helping students in class or students from other research groups, I'm always writing stuff like this out. I'm always sketching. I'm always drawing stuff out, crossing things out, erasing it, and so forth. I doodle a lot when I am doing this sort of stuff, and I strongly suggest you do that as well. Okay, if you're not in the habit of doing that, writing this little bits of information down so that's sitting there right in front of you, so you can glance back at it and go, oh, that one unsaturation and the groups and so forth, that can often be extremely helpful when you are trying to solve a structure. Okay, so this is a reasonable structure right here for this molecule that fits the C7H14O formulation. There are other molecules you could draw that have that formula with one unsaturation. You could draw ketones and so forth of various types from the structure. But a ketone, okay, for example, 1, 2, 3, 4, 5, 6, 7. Let's put a ketone in, okay, right there. And all the other positions are occupied with hydrogens, okay? Now, you could draw that molecule. It has the right formula, it has the right number of unsaturations, but notice it's not symmetric, but it would have to have 2 carbons integrating to 3 each. And we don't have that. We have a carbon integrating to, or a proton group integrating to 1, okay? This molecule would not feature that, okay? And so that's why this structure, while matching the formula and the unsaturations, does not match the observed hydrogen integrations, okay? So all of that information has to come together in order to, have all the information converge on just one structure. Another alternative structure that you could draw another ketone would be to, and I'm just going to use my fingers here and make a mess on the board, is to draw a structure like that. That's another one that has the formula, the unsaturations, but that one's symmetric. This one would show only 1, 2, 3, 4 distinct carbons. It would show only 3 distinct groups of hydrogens, and they would integrate apparently 3 to 2 to 2, which of course would be 6 to 4 to 4 after you take into account the symmetry. Okay, so every bit of this information helps lead you to this and only this structure. Okay, and other alternative structures have something that does not match with the information gleaned from just looking at the groups and integrations of the proton and carbon NMR spectra. Okay. All right, on to the second example, a little bit with a magic eraser, and be right back. All right, the second unknown is the formula C8H4O3. Okay. And doing the index of unsaturation calculations, 8 carbons minus half the number of hydrogens, okay, 4 of them, no halogen, no nitrogen, plus 1. 8 minus half of 4, 8 minus 2 is 6, plus 1 is 7. 7 unsaturations in this molecule, okay? That's a lot. That's a lot of unsaturations. Aromatic rings almost certainly called for here to get that many unsaturations with, a relatively small number of carbons, with 8 carbons. And a quick glance at the NMR spectra shows, sure enough, peaks around, in that 7 to 8 or so ppm range in the hydrogen spectra, also around 120 in the carbon. Yeah, we're definitely looking at an aromatic molecule here, okay? And so let's make note of that. Okay, so this thing's aromatic, okay, with a lot of unsaturations. There's more than just a benzene ring in there. That gives us 4 unsaturations. There's 3 more to go. So more double bonds or rings and other things like that in this molecule. Now, we look at the groups and integrations. And we look at the hydrogen spectrum for a moment, and what we see there are, for the hydrogens, only 2 groups. And they integrate 1 to 1. Okay, on the spectrum. 2 groups integrating 1 to 1. There are a total of 4 hydrogens here. This only adds up to 2. In the back of your head, a little bit of warning, warning there might be some symmetry in this thing, okay, because the integrations are not adding up to the total number of hydrogens, adding up to half that number. So symmetry is a likely issue here. But before we get ahead of ourselves, we are going to do the look at the carbon spectrum. And what we see are 4 distinct carbons. Now, once again, the formula tells us there are 8. What we see is 4. Okay, and so once again, we are looking at a strong indication of symmetry. Okay, this molecule is symmetric. And remember, symmetry has the effect of taking, a relatively large molecule and reducing the number of distinct hydrogen groups, reducing the number of carbon groups, interfering with the integrations of the hydrogens, making everything simpler and seem like it's a smaller molecule than it really is. Okay, so this thing is symmetric. Now, one way that you usually think about symmetry as aromatic molecules are very distinctive this way is start sketching things, okay? And I'm going to go right ahead and draw myself a benzene ring, alternating single double bonds. And I'm going to indicate clearly one of its planes of symmetry right here. Now, I can make a very strong case that this molecule with only 4 hydrogens in it, and they're all aromatic, that this is a ring that looks something like this. Okay, here are the 4 hydrogens, but the hydrogens are on opposite sides of the mirror plane. Okay, there's one group integrating to 1, but it's really 2. There's one group, it integrates to 1, but there are really 2, so I'm going to kind of modify my integrations and say 2 to 2, and that's all I can say about the hydrogens right now. Now, doodling this thing a little bit, because there's a lot more to go here in this molecule, I'm going to put this little dash line in and say we know there are 2 hydrogens on each side of the mirror plane here, of the symmetry element. That there are also 4 carbons on each side of this mirror plane here. Now, look at it carefully. This that I know I'm certain about gives me 3 out of the 4. Okay, I get 1 group here, 2nd, 3rd group. Okay, but there must be a 4th group of carbons that are on opposite sides of the mirror plane here. I have these little lines not going to hydrogens, going to the rest of the molecule, and okay, it is a reasonable guess that there are carbons up here, okay, and there are now 1, 2, 3, 4 carbons on the right side of the mirror plane, 1, 2, 3, 4 carbons on the left side of the mirror plane, okay, equivalent to each other. Okay, and that gets me all my carbons and all my hydrogens, but I still have 3 oxygens to put in here. And 3 oxygens presents a bit of a challenge, okay? Because it's an odd number. How do you put 3 oxygens in to maintain the smear plane, to maintain the symmetry? For example, If I put an oxygen on each side, there are two of them, but I've got to put the third one in there. Where do I put it? If I put it on the right side of the mirror plane, I've broken the symmetry. There's two oxygen on one side, one oxygen on the other. Similarly, if I put the oxygen over here, I have the exact same problem. Okay, this is a bit of a challenge. Where should we put that oxygen? Yes, indeed. Some of you saw it already. We're going to put it on the mirror plane. Okay, if we put it on the mirror plane, then that oxygen maintains the overall symmetry of this thing. So I have to put 3 oxygens in my structure here. I have to put in 3 more unsaturations, and with just these carbons and these oxygens, that's all I have to work with now. Okay, given all the constraints here, okay, I've got to have 3 more unsaturations to get to my 7. There's 4 of them here in my benzene ring. I've got 3 more to go. I've got to put 3 oxygens in where one of the oxygens is on the mirror plane. It has to be right there, okay? What else do you do? The only thing you can do, pretty much, okay, given the rules of chemistry and organic chemistry and the number of bonds that form, there it is, okay? There's the structure of this thing, okay? It preserves all the symmetry. It gives me 1, 2, and then the ring, a 3rd unsaturation in addition to the 4 of the original aromatic ring. There's the structure. It's the cyclic anhydride. You know, I'm sure this molecule has some long-ass organic name rules and stuff. It's a aromatic cyclic anhydride. That's what that's my name, and I'm sticking with it. And so there is the structure here, and there's the only structure that matches all of these characteristics that we derive from the NMR spectra, okay? And outside of looking at, recognizing that we had an aromatic, hydrogens on an aromatic ring, that area around 7 ppm, that's the only thing we've looked at outside of just simply the number of hydrogen groups, their integrations, and the number of carbon groups, okay? We quickly realized this thing is symmetric, and using that information, we can start putting together the rest of the molecule. So remember, when you're doing this, don't break rules of organic chemistry by, trying to come up with, some bizarre structure that has 8 bonds on a carbon or something like that. 3-membered rings are certainly possible, but rare. And so invoking a 3-membered ring is a bit dicey in structures like this. 6-membered rings, 5-membered rings, they're far more common. And so remember all your rules of organic structures while you're doing these. And generally what will happen is as you start looking at this information, start sketching out little pieces like this, suddenly one structure and one structure only, boom, will snap together, and you'll realize that it matches all the criteria present. To be honest with you, the first 100 structure solving problems that you do are the toughest, okay? It gets easier after that. Okay, I'm slightly exaggerating, but not really. This is one of those things that it really just takes a lot of practice. And so just about every single assignment we do from here on out is going to have these, a couple of these problems assigned, attached to it, simply because there's no other way to learn how to do this than to do it, okay? Just to practice it, several times until finally you start to see the patterns involved. We start adding, as we move along, additional layers of interpretation, the chemical shifts, the coupling patterns, and other fancy experiments that we can do in NMR. But you get a lot of mileage out of just groups and integrations, okay? And I hope these 2 examples help make that a little bit clearer. And so keep that in mind and practice a few. Talk to you later.